Hello and welcome to this InfoShare. We would like to present to you the results of an incubator project that we did. The title of this incubator was Long Haul White Rabbit Time Service, and it evaluated the deployment of high accuracy time service using White Rabbit technology, sharing the same long haul fibers as existing optical DWDM networks. We did this work as a part of the technology task, which is task one. And this task is part of the network development work package, which is work package 6 in the GN5-2 project. We will have three parts, three presentations. We will first start out with the theoretical part. It will give you details of what the incubator set out to achieve, and it will be followed with a more practical part dealing with lab tests and the field trials that were conducted. And in the end, we will hear a third presentation, which will cover cost implications for NRENs who would like to implement such solutions. Please save all your questions until the very end. We will have a question and answer section in the end. And you will be free to ask your questions either directly by raising your hand or by putting it in the chat. So the InfoShare will be recorded. We will make the recording available in a few days. You will find the recording as part of this events page. So let's now start with the first presentation. This will be done by Raimena Veisllari from Sikt, the Norwegian NREN. She was the leader of the incubator project.
Okay, so I'll start with a short description of the project. We started in April last year, and we wrapped it up in February this year. It was initiated by GÉANT, Guy Roberts. It led it at Sikt, and CESNET carried on all the tests in the lab and in the field, and then with contributions with SUNET, FUNET, and GAR. So we set out the goal was to learn from experience and current deployments of White Rabbit and focused on the long-haul transmission, sharing it with DWDM legacy fibers. Because a lot of work has been carried on during previous GÉANT projects on OTFN tasks. However, we saw that there is a missing piece, this bidirectional long-haul over DWDM links. Of course, the key requirement is coexistence with our, so White Rabbit, it's on-off keying, high power. Modulation need to coexist with coherent high-speed signals, 400 gig, 800 gig in the future, without impacting the data traffic. And the objectives then of the project was, okay, we ran a survey to get the update on the both deployments, but also who is planning and how White Rabbit time service deployments in the future, and European NRENs and NMIs. And in parallel, then, if we evaluated regeneration techniques in the lab and in the field for bidirectional transmission. We have a cost model of these techniques and wrap up with recommendations and for best practice on how to deploy it in NREN networks. The main deliverable of the project is white paper. It was published today. You can find it on this link. It will be also available in the InfoShare description and will be sent afterwards together with the presentations and the recording. And you can see here, it's very simple illustration in the map of how it looks, the field trial. This was run on the GÉANT link Prague to Vienna on 3 inline amplification sites, and then look back to Prague to do the performance measurement on the same site where the Grandmaster is. So we ended up with circa 500 kilometer optical line. But Jaromir will go in technical details, both of field trials on the second part and the lab tests. Disclaimer important, we did not consider calibration techniques. In the white paper, we have discussed briefly, give you an overview on what are the calibration methods, but we did not focus on that. We did not run pre-calibration of the system since we had the time service endpoint look back to the grandmaster, we could do performance measurements, so relative performance comparison. Okay, the Infoshare structure, Susanne already talked about it. I'm starting with very high level. What are the challenges and the solutions, and a bit on the highlights on the survey. And Jaromir will go through the tests and results and guide with the cost model and the most important part, the recommendations for NRENs. Okay, so starting with the first refresh. So when we talk White Rabbit protocol, of course, it was developed by CERN in 2008. So extending precision time protocol, the IEEE 1588 standard of 2008. Now it's available as high accuracy profile on the 2019 standard. Key enhancements to PTP. First is the clock synchronization. So you lock the frequency of the clocks of the slaves to the master to minimize the drift using synchronous Ethernet, SYNC-E, the ITU-T profile. Then you do enhancement of the timestamp precision through phase measurement. And important for us coming from the optical network domain, it's the evaluation and compensation for the transmission link asymmetries and the error introduced in the offset because of it. Open source, commercially available. There are system vendors that offer the switches, being that it was designed for LHC, so it was metro network, 10 kilometers. It's being deployed for hundreds of kilometers. We have examples in NREN networks. For long haul, the standard at this point, its requirement is that you maintain sub-nanosecond time accuracy from 14 to up to 20 nodes in a chain. And of course, for frequency at the picosecond level. But we are in this project, again, we are focused on the time service, not frequency. Wanted to highlight, of course, there is more information on the White Rabbit collaboration website, but wanted to highlight that in 2 weeks, it's actually the White Rabbit workshop, and you can register. And if I'm not mistaken, it will be also live streamed if you're interested. So now moving on the optical network side. Another simple refresh here. It's okay, we talk about optical dense wavelength division multiplexing for transmission of our data. The system is designed on communicating with fiber pair. So we use one wavelength between endpoints, for example, the green wavelength between 2 endpoints, but one-way direction. So left to right on fiber A and on the way back on fiber B on the same wavelength. So this is what we call unidirectional transmission or two-fiber transmission. The data services are provided as alien wavelengths, so we can use the same service, alien wavelength, also for our White Rabbit time service. So basically, the key advantages here all of them come from the fact that we are using the same DWDM components as for the data services. So we are using standard SFPs, and we are, especially for long haul, we are using the same amplification sites, nothing extra, for regenerating the signals for long haul transmission. The key disadvantage, the way that we look at for achieving, we're talking about high accuracy, so nanosecond level accuracy. The key disadvantage is the asymmetry introduced by the fact that different fibers have different lengths in practice in the field. Another refresh. So how does White Rabbit and PTP actually calculate the offset in the clocks of the slave to the master and synchronize the slave to the master? It's true, this is very simple, basic PTP message exchange. So at point T1, the master sends a sync message with this timestamp when it sent the message. That is received at the slave at T2. The slave at T3 sends a delay request message to the master that receives it at T4. And then the master sends this T4 in a delay response message to the slave. So at this point in time, the slave has 4 timestamps and then can calculate the offset to the master. So if we look at T1 to T2, this includes the path delay from the master to the slave, but also the error, so the offset of the slave clock. So T2 minus T1 will include both the path delay and the offset. Now, what is the path delay? As I said, the problem with PTP was this, that it assumes symmetric path delay. It's what we say the mean path delay is the round trip time divided by 2. So delay master slave, T2 minus T1, plus delay slave master, T4 minus T3 divided by 2. The problem is, of course, is the asymmetry, that not the delay, transmission delay on the two directions is not equal. And what we call asymmetry. So there will be an offset that we calculated, but a better enhanced offset will be if we know the asymmetry, then we have also the error introduced by the offset, the asymmetry, and we remove that from the calculated offset. So that was PTP. But why is this unidirectional issue? Is that realistically there is, as I said, different lengths between the two fibers. Rule of thumb, how does this translate? It's rule of thumb, transmission speed of light in the fiber. It's 2/3 of speed of light in vacuum. So it's circa 4.95 nanosecond per meter. So as an asymmetry of 1 nanosecond translate in fiber difference in length of 20 centimeters between fiber A and fiber B, which is very short. In practice, we have measured, for example, in Svalbard, we own the cable, so we have better control of the cable and the fiber lengths, but we have measured in the range of 15 meters. Every time that you have a fiber break, you have a third party that maintains the fiber. You do not know how they will splice it and how many centimeters or meters it will change. So that is what we call the unknown asymmetry. So after every fiber break, you will need to recalibrate your network, remeasure, let's say, the offset, which is impossible. It's not practical in our networks. That's why the solution then we focus on bidirectional transmission. And this is, of course, the standard, the original CERN methods, which is based on DWDM, so wavelength division multiplexing. You have a dedicated fiber and two different wavelengths, 1310 and 1490 nanometers. So also the White Rabbit protocol is designed for bidirectionality. However, we are in dense wavelength division multiplexing, so we are on the C-band optical spectrum. And what we can do then is that we can use two consecutive wavelengths of our ITU-T 100 gigahertz spaced channels for different directions. So in this case, illustrated in red, it's master to slave, and slave to master illustrated in blue on fiber A. So we remove the unknown of the different fiber lengths. It's the same fiber length. However, there is still asymmetry, which is introduced because we have what we call chromatic dispersion, that different wavelengths travel at different speeds in the fiber. This is in standard fibers, usually around 17 picosecond per nanometer per kilometer. As I said, if we use the ITU-T spacing, we have 0.8 nanometer between the two wavelengths. Translates in around 13.6 picosecond per kilometer asymmetry. So if you compare, it's 14 picosecond versus per kilometer versus nanosecond per 20 centimeter asymmetry, right? So the accuracy levels are completely different. So you can then measure this in the lab and compensate it, so calibrate the system and compensate it in field automatically. White Rabbit does this, so you don't actually, it's independent of the fiber length. Okay, so this was a very general overview on why we are looking into bidirectional transmission. What we focused on the project, it's further on long-haul bidirectional transmission. What we talk about long-haul is that since we have hundreds of kilometers. You need inline amplification sites. So every 80 kilometers, your optical signal fades. So every circa 80 kilometers, you regenerate, amplify the system. These are systems for data DWDM, which is unidirectional. So the amplification sites also do amplification in one direction. It's unidirectional. So this is very simple illustration. For example, let's say we have EDFA amplifier. For fiber A, it will be left to right. For fiber B, right to left. What is the problem? Very simple, that the red wavelength here will be amplified while the blue will not. So we need new systems that are bidirectional, giving us bidirectional regeneration. Further on, if you have bidirectional transmission, you can use the second fiber to loop back the signal, and this is what we have done in the field trial, to be able to receive the time service where you have the grandmaster to actually do performance measurement with a simple analyzer. Of course, this will be more expensive because you need double the components. But if you want to get an understanding of your performance, of your time service that you are delivering. Okay, so then what are the regeneration techniques that we have for bidirectional transmission? And we have also covered in the project. We start simple, what we call 1R. You do all optical regeneration. What you do in this case, this illustrates the original signal, zeros and ones, on-off keying, for example. And then after 80 kilometers, your signal has attenuated, so you can't make a difference or can't differentiate between your ones and zeros. So you need to actually amplify the amplitude, and you can do this all optically. So we have used EDFA bidirectional amplifiers in the field trial in the project. Of course, key advantage here, it's all optical, so you're avoiding electronics, so you remove the jitter. But of course, you have phase noise on the optical domain that will be accumulated. So that's maybe a part of the disadvantages of the system. So at some point, after so many units of amplification, 5 to 8, we have identified, you will need to move to the electronic domain to regenerate the pulse shape and maybe the timing as well. It does not need calibration. It does not change, does not add to the fiber length asymmetries or asymmetries as such. You can also multiply multiple white rabbit signals. The disadvantage is that depends also a bit on your band, the spectrum you are using, C or L band, but it is not a standard component as it is we use for the data transmission. So the availability might be lower, so the cost might be higher. Guy will go in more details on the considerations and recommendations of the pros and cons of these techniques. The way we have also illustrated in the white paper, White Rabbit Grandmaster switch, we're adding on the fiber A signal. In the amplification side, we need to drop the signal to send it to our bidirectional amplifier and reinsert it on the way further on fiber A, and vice versa. We have to drop and reinsert the signal. So basically here we need to have filters to remove the White Rabbit signal or wavelengths. The second regeneration technique, it's optical, electrical, optical, OEO. This is very simple media converters, back-to-back SFP, so low-cost systems. What you do on top of the reamplification of the amplitude, you do reshaping. So here, basically, you recover the steepness of the pulse, but if you see the difference, you're not doing retiming, right? So you're not touching the clock signal. But of course, you are adding the phase noise, not only of the optical line, but also of the device itself. And this is accumulated for each node. It is So it needs to be calibrated, pre-calibrated for optical performance. Disadvantage, it's that not necessarily these are media converters, so you have to think about that you need carrier grade requirements with OAM, cooling, dual power, and so on. But it is low cost and low technical complexity. And the same as bidirectional system, you just drop and add and regenerate with the OEO device. And the third and the last, it's regeneration with White Rabbit switches. So in the diagram here, you can see, so on top of reshaping, so re-amplification, reshaping, we do retiming so that the node itself will synchronize to the master and best guess retiming of the original or of the received signal. The advantage is that, of course, this is the simplest method. We already have White Rabbit switches in our system. We have OAM. Everything is integrated to provide White Rabbit-based time service. So you just add a switch as a regeneration node. But this also means that if you are actually not providing time service on that add drop node, but it's just a ILA site, you are just using it for regeneration, the system will end up being higher cost. And being that you are doing retiming, you are also adding the jitter, accumulated jitter per each node in the chain. And it's the same model that instead of OEO or BD you are adding a White Rabbit switch in the ILA sites. So these three techniques are what Jaromir will present, and Guy will further discuss on pros and cons and considerations. So lastly, a few highlights on the survey. So the survey is part of the white paper included as an appendix. We ran interviews and also offline questionnaire with NRENs and NMIs. So deployments, it's SURF, Renater and RFMev together in France, CESNET in Sweden, SUNET providing optical network with NetNode and RISE providing timescale, FUNET and VTT in Finland. We have Switch, NPL and INRIM, so in more detail. And then also discussed with NRENs that are in the planning evaluation phase of White Rabbit Time Services, BailNet, Asset Sikt, NorduNet. We are currently running pilots with the Nordics, interconnecting the NMIs and Asera. And how it looks in terms of architecture, the preferred is still the shared fibers with DWDM. It's lower cost systems. However, there are the NMIs that have the dedicated dark fibers for high stability frequency transfer for optical clocks like Pathfinder. And there, of course, you can multiplex the White Rabbit time service. In terms of unidirectional versus bidirectional, we see that both deployments are equally present, and further on moving towards more bidirectional deployments. In terms of spectrum, what optical wavelengths you are using for White Rabbit, just a reminder, this is how it looks. So the DWDM systems for data channels, we are currently using the C-band range, but new systems are also A-band ready. And you can use the edge of the C-band for White Rabbit, the on-off keying, and have a guard band towards your data on only one side. But also you can use the L-band where you have a wider gap to your data services to not have the cross-phase modulation and other non-linearities. In terms of regeneration techniques, White Rabbit switch is still the most common. But we see that it's also, of course, depends on the size of the network. The Nordics, both SUNET and FUNET, they have long haul links, point-to-point White Rabbit connections. And there they are using OEO regenerators. And CESNET is using the Checklight BD amplifiers, CDFA-based. Network size, it varies quite a bit. This is a good example with RFMev. They have divided in three areas, let's say, or hierarchical sizes. You have the edge to your customer in the few kilometers, then moving to regional in tens of kilometers, and then the national links on average are between 200 and 300 kilometers. So this is between White Rabbit time services or a drop of your time services. But of course, as I said, at FUNET, you have also links that are up to 800 kilometers. This is the longest one, but implemented as an alien wavelength. In terms of size of White Rabbit networks, we see that we are at the tens of nodes, but also there are networks that are being planned up to 100 nodes, both Refimev, but also us at Sikt at a very early stage are looking that the network, if it's national time service, it will need more than 100 nodes. Accuracy range also varies quite a bit, but we are at the level of sub 100 nanoseconds. So, for example, CESNET, its maximum, it's GNSS or better, so 40 nanosecond. For research, we go on the sub nanosecond, but also on average, for example, Refimev is providing a service of 10 nanoseconds. So it also varies quite a bit. Okay, so this was my part. Now I'll move or give the floor to Jaromir with the lab test and the field trial.
Hello, my today's technical part of the presentation, I prepared information about lab tests and also field test. Also, as part of the lab tests, we verified the possibilities and measured the stability of the transmission of White Rabbit time signals and their degeneration on long optical paths. All lab tests were performed on 4 times 100 kilometer optical fibres. We worked only with bidirectional transmission on a single fiber. Under same conditions, we tested 3 possible White Rabbit signals regeneration technologies for long roads. Firstly, it is 1R regeneration with only amplification of the optical signals using bidirectional EDFA optical amplifiers. And also we tested the possibility of using Ethernet OEO optical to electrical to optical media converters, SFP to SFP transceivers. And finally, we also verified the possibility of repeating White Rabbit signals using White Rabbit switches themselves, both at the beginning and the end of optical path. For the field test, we used a real GÉANT line on the Prague-Vienna road, where GÉANT transmits 2 coherent data DWDM signals, each with a speed of 400 gigabits per second and using Infinera system. For this field test, we used only one variant of amplifying the White Rabbit signals using bidirectional EDFA, where in the final phase of the field test, we used 5 pieces of these bidirectional amplifiers over a length of 498 kilometers. In the test, we used the standard open hardware White Rabbit switches type VRS 3/18 version without or no low jitter version. Also, we used the precision time interval counter from Stanford Research System and rubidium clock also from Stanford as a signal source. For PD EDFA, we used SDN checklight series from our CESNET development, which were supplied by our industrial partner, the Genesis company. In the lab test for OEO generation, we used SFP to SFP media converter cards from CTC company. And also all tests, including the field test, we use the same DWDM SFP optical transceivers, 1 gig Ethernet for L-band channels, number 8 and number 9 for 120 kilometers length. For this, the appropriate DWDM L-band 100 gig filters and also DWDM for skip zero filters, bandpass filters. So we also used for the field test. We also used the other component Ethernet switches and SFP transceivers for the necessary management on the path as CWM filters, SFPs, etc. The concept of connecting all tests is shown in the figure. Between the master and slave white rabbit switch, an optical path with tested repeaters is inserted into the loop so that we have beginning at the end of the path in one place. Using precise time interval counter, we can directly compare the time signals at both ends of the path. The values from this counter are transferred to the PSDB time series database using small microcomputer. The individual statistics then proceed using connected computer. And using the Grafana software, we also display the other data in real time, such as the power levels of the optical signals at individual points, etc. All tests were performed in this way for several weeks to verify the long-term stability of the solution. Yeah. There are the specific connection of the lab test with total 3 pieces of BD EDFA on optical path of 4 times 100 kilometer of fiber of optical coils. The beginning of the path is equipped with one white rabbit switch as master, and at the end you can see the white rabbit switch as slave. The standard 100 gigahertz DWDM filters for channels 8 and 9 combine both wavelengths into one fiber facing each other on both ends. Standard splitters are installed at the end of the road, which branch 5% of the optical power from both sides of the fiber for connection or on optical spectrum analyzer during the operation. Bandpass filters we also used for each BD EDFA amplifiers, which allows the possible integration of standard C-band DWDM data signals or even the transmission of precise frequency signals. We use this type of bandpass filters also in the CESNET network. Another lab test uses the same wiring and the same components as previous one, only 3 pieces, simple OEO SFP to SFP media converters were used as wide rabbit signal repeaters instead of BD EDFA. In this time, additional SFPs, the L-band transceivers were used in these media converters, which types are already used in wide rabbit switches. Similar, the same types of DWDM 100 GHz filters were used to combine the transmission directions into a single fiber. The last type, last type of the lab tests uses the wide rabbit switches for generating and repeating of time signals. So in addition to the amplification and reshaping of the signal itself, there is also a renewal of time information retiming. If we consider a master switch as signal source, we receive the time signals at the end of the road after a series of 4 pieces white rabbit switches. Other components is the same as the previous test. We implemented the field test on a real GÉANT route where the DWDM system from Infinera is already in operation. As we can see in a simplified connection diagram on Infinera ROADM and amplifier cards, then Infinera system already has built-in L-band filters, DWDM L-band filters. Since the L-band is not commonly used and is not used here either, we could use these built-in filters with great advantage directly to connect wide rabbit time signals with existing traffic on the road. We use the same L-band DWDM transmission channels as in the lab tests. We could perform all the work in this field test without interrupting the operation. In practice, such filters are not already present on the road. They would have to be installed, and this would interrupt the data transmission. And last image shows the transmission spectrum in Infinera system. Individual Raman pumps are shown here, and wide rabbit signals, it's 2 wavelengths, is located in the L band near the C band and slightly amplified by Raman. And we added also OSC channel at 1590 nanometers CWM because we needed remote monitoring with the EDFA amplifiers. Here we can see the actual complete connection of the field test on road Prague, Vienna. We tested again in a loop as in the lab test in 2 steps. First step, for the initial verification, the loop was closed in the Šachotín location via nodes Prague, Kouřim, Šachotín, and back Kouřim and Prague via the second fiber. And total length of the loop 1 was 322 kilometers, and 3 pieces bidirectional amplifiers were used. After verifying stability and function of the time signal transmission, we extended the loop in step 2 through Prague, Kouřim, Šachotín, Ivančice nodes and back through Šachotín, Kouřim to Prague along the second fiber. This second loop with length of 498 kilometers had a total of 5 pieces BD-GFA installed as white rabbit signal repeaters. Since the Infinera system also used Raman amplifiers on the road, the amplification in both direction of the BIDI transmission was slightly asymmetrical. It was about 2 or 3 dB. Because we didn't have IP connectivity in these amplification nodes, we used regular Ethernet switches with SFP ports, CWM transceivers, and filters to add OSC channel on the wavelength 5090 nanometers CWM. We used the same components in both of the lab and field tests, and we can then compare the results of with each other. Each test was run over many days. A period of 5 days was chosen for this analysis. All tests were connected in loop, where we always had a start and end of the route in one place, and then we didn't have to calibrate the system because it's only fixed value. And we monitor the variability and time deviation and stability of the time signal on the route, where for better and easier reading of values from the precise time counter, we always needed to have positive number available, and this was next reason for no calibration decision. And in a real use, only at the end-to-end point calibration is necessary to achieve the required accuracy of time transfer, because it's not in the loop and it's a line. And in the test, we monitored 3 main key parameters. Histogram is a graph that shows a relative number of samples in a given interval of values and provides a very good overview on the performance of the time transfer. The time deviation, TDEV, is used to determine the quality of time signals in a given averaging interval. According to White-Rabbit specification, the error should be less than 1 nanosecond. And because the TDEV is averaging based statistic, it can hide rare occasional events where the target accuracy is not achieved. And for this, the parameter MTA, maximum time interval error, is better for showing the and measure stability of time signals, indicating the maximum peak-to-peak error in a time interval. And MTA is thus an indicator of the worst possible error. And here we can see histograms of the results of individual lab tests. BD EDFA, SFP to SFP converter, and using White-Rabbit switch as repeaters. The histogram provides a brief visualization of measured offset distribution. All 3 histograms look like Gaussian distributions, but have different standard deviations. The x-axis is the same for all graphs to allow direct visual comparison. In this page, you can see here we can have 2 graphs for TDEV and MT values with results of all 3 lab tests. The lowest curve in the graph is always for BD EDFA amplifiers. It's purple color, and middle curve in the graph, green color, is the for the test using SFP media converters, and the highest curve in the graphs, blue color, shows TDEF MTA values for using wide rabbit switches as repeaters. Here is clear confirmation that use of BIDI EDFA amplifiers brings the best results in transmitting wide rabbit signals over long distances. For the field test, it was important that added wide rabbit signals did not cause a degradation of the existing data transmission on GÉANT network. This is coexistence of coherent DWDM 400 gigabits per second data signals transmitted in the C-band and with slow on-off keying, 1 gigabit per second modulation signals that are added to the DWDM in the L-band. And when monitoring on Infinera system, there was no observable degradation of the data signals when adding wide rabbit signals to the path during operation. We observed the prefect bare parameter, which is errors before their correction, was monitored on the coherent receivers on Infinera system. Also, the measurement of the spectrum of data signals using optical spectrum analyzer days in detail confirmed that were no changes in spectrum and transmitting data. We monitored the changes in both phases of the field test, both during the first connection of the shorter loop 1 and for the final field test with total 5 pieces BD EDFA amplifiers installed. Here, since the field test results for the first and the second loops were very similar, we present the results of the final loop 2 test itself in the graphs and in the graphs below. There is histogram for loop 2 with 5 pieces BD EDFA on the for route length of 498 kilometers. For the field test, here you can see also graphs TDEF MTA values with comparing with lab tests. You can see results of in this field test with purple color with 5 pieces BD EDFAs at 498 kilometers are visible, and you can compare with a lab test. Field test was green and a lab test is purple. With lab test 4 times 100 kilometers with only 3 BD EDFA, and slightly worse result of the field test in terms of time stability than the lab test can be explained by the larger number of BD EDFA amplifiers over time. Also, the daily temperature changes during the test autumn to winter last year were higher on the fibres on real road than during the test in the lab conditions, of course. What can I say? At the end of my technical presentation, I would like to summarize our results. We have to say that all tested methods of transmitting wide rabbit signals over long distances are very well applicable. All types of techniques. The best results in transmission stability when using BD EDFA amplifiers. Of course, there are limitations due to their physical properties, and we cannot use a large number of these amplifiers in a series for this reason. Next in order in terms of transmission accuracy is the use OEO SFP to SFP converters. And last, in terms of parameters, is the use of wire bit switches as time signal repeaters. Even so, it can be said that cascade of 4 wide bit switches, not counting wide bit master switch, still guarantees a defined transmission accuracy of below 1 nanosecond. In our field test, with 5 BD EDFAs on the road, 498 kilometers, approximately 500 kilometers, and total attenuation of 118 dB, we achieved wide bit signal transmission stability accuracy better than plus minus 100 picosecond over several weeks of measurement. And if we convert the 100 picosecond difference into the length of that the light travels in the fiber, we get only 2 centimeters. So the signal transmission accuracy in the fiber was better than plus minus 2 centimeters in the field test. And at the end, I could also share the information outside the incubator. At the CESNET, as the National Research and Education Network, we have been transmitting precise time and frequency for several years for some partners. And this year, we started the deployment and installation of wide bit technology in full scale in our network. We are using the same techniques when we presented BD EDFA technology in L-band to amplify wide bit signals along with data traffic in C-band, and by the end of this year, a precise time will be available as a standard service to our customers and partners across the whole network in 20 nodes.
Thank you. I'd particularly like to thank CESNET, actually, a very thorough lab and field trial testing and the extremely good stability results over 500 kilometers of fiber. And just to say that it was a relatively easy install in that in the equipment we use, which is the Infineon equipment, we had L-band filters built into the equipment. So we just connected the bidirectional amplifiers onto that L-band via some filters, and that was the equipment on site, along with the management switch. So a very nice piece of work. So I will let's see. What I want to discuss is try to give a sense of what it's like to actually deploy White Rabbit in a real DWDM system, and what the considerations and costs are that need to be evaluated before you can begin. Helpfully, Raimena covered the survey we did of NRENs, and if you look in the report there, you'll see what the different NRENs have deployed in their networks. So there are many considerations that you want to keep in mind when deciding how to deploy White Rabbit in your system. So a mix of DWDM and a White Rabbit signal. So careful design is needed. One of the first ones, before you even decide which type of technology, so the three technology types we talked about, is where to place it in the spectrum. So there's a C-band or L-band options, and then once you decide that, what type of regeneration, 1R, 2R, 3R, and then you also need to be cognizant of the need for guard bands to ensure no degradation of traffic. So in the field trial, we by default had guard bands because we put the White Rabbit in the L-band, which was very convenient. So let's try and untangle the cost implications for this. Now, as Raimena pointed out, we have for DWDM the ability to use channels in both the C and the L band. If you choose as an NREN to try and use the C band, maybe because you don't have access to L band filters, you have to keep in mind that you may use up some of that spectrum that could be provided to your customers. So L band will save you that cost. And as Jaromir said, we very successfully used their bidirectional L band amplifiers. They are relatively low cost, as I'll discuss later. So if you've got L band, it's a great option. We discovered. Things to consider is new build versus retrofit. If you've got an existing system and you want to retrofit White Rabbit, it will require filters to be added if they're not already there. So there will be some cost disruption to put these bidirectional filters in. Now you can, there's another option there where you can actually just use a plain old alien wave channel, but the accuracy is going to be much less on that. If you look at the White Rabbit report, you'll see that that's a technique used by Refimev, and they were looking in the order of 10 nanoseconds accuracy. So we're looking at two orders of less precision in terms of time distribution. So guard band is the one which is potentially a little bit tricky. Deciding the appropriate guard band should be done, but we're in conversation with your equipment provider, and it will depend on how much loading of wavelengths you have in your C band, and how much optical margin is in the system, and so on. So something that you need to consult with your equipment provider. So what I'll do is just run through the three technology types and look at the practical considerations of each. As Jaromir pointed out, the best performance available with rapid convergence time or averaging time down to 100 picoseconds was the bidirectional EDFA amplifier. Relatively low cost if you buy these from the Czech technology, but will be probably more expensive than if you put OEO converters. We'll look at the pricing later, but in particular, the thing to keep in mind is that a long chain of amplifiers can potentially become unstable, and the power level, the signal to noise ratio accumulates. So you will need 3R regeneration after around 5 amplifier sites. Also, we discovered quite interestingly that even if you have Raman in the C band, that gain can leak into the L band, and certainly if you have Raman in the C band and you're using the C band for White Rabbit, it can cause asymmetric gain because it's counter-propagated in one direction. So the transmission in one direction will have a slightly different gain to the return direction. So you need to evaluate your optical power levels in your system to try and understand the risk of asymmetry. And also the risk with bidirectional amplifiers is gain oscillations. That's a possibility if there is reflections present on the fiber. So typically what happens is if you have a dirty connector, a low-grade connector, so something like a LCPC, you can get reflections. So what we recommend is the use of angled connectors to reduce that, and I'll talk a bit about that some more. And you also want to keep the amplifier gain as low as possible to to reduce the risk of reflection. Cost effectiveness for the 2R repeaters. Now, we have found that they can be cost effective, and the performance, while not as good as the bidirectional amplifiers, is still pretty good. The advantages of using 2R regeneration is that at every OEO site you can change wavelengths. You probably wouldn't want to do that, but it gives a bit more flexibility. Thing to keep an eye out for is carrier grade. So there's a lot of quite cheap devices out there you can buy. There's a cheap device from Taiwan that's readily available, but these aren't carrier grade. So if you want to build a carrier grade solution, you want things like OAM, dual power supplies, remote management, and so on. You have to be very careful about what you specify there, because that's going to be trip you up there. And also cooling. I'll come back to mention that again, but we've found that some of the cheaper OEOs without fans can have a problem with being unable to cool these high power DWDM pluggables. So that's the 2R regeneration, and then the 3R, which is basically you just put a white rabbit switch at every amplifier site. And interestingly, that's the solution that Surf has gone with, on the basis that Netherlands is a small country and most hops don't have to go through many amplifier sites. So they more or less want 3R regeneration at every site to access it. So if you've got shorter links, 3R regeneration with white rabbit switches works pretty well. Does reduce the performance, so it was the worst performance on long links, so probably not advisable if you want a long link of 1,000 kilometers, and more expensive than OEO solutions. So that's that. So what we did as part of the incubator is we came up with an Excel cost calculator, which we will make available for everybody to look at. And so you can use that yourself to try and predict the cost of White Rabbit to your DWDM system. So you can add parameters such as the number of years of terms of your lease, number of amplifiers on site, number of 50 gigahertz guard bands you plan to use. Do you want to use a carrier grade White Rabbit or a standard White Rabbit? Filter costs, amplifier manufacturers, and so on. And once you enter all that, there's 5 scenarios there which we've analyzed, and these are essentially the center 3 are the ones, numbers 2, 3, and 4 in that scenario are the ones that have been described here, and the ones were trialed in both in the lab and the field. We also, for costing purposes, added 2 more, an alien wave. So that's where you just build a multi-hop bidirectional system. So just a standard 50 gigahertz alien wave service, and you put White Rabbit on that. That is actually the solution, as I said, being used at the moment in the RefMF network. And we've also costed up LSTAB, which is an alternative solution provided by a Polish company called PickTime Systems. So how do the costs look? So in the graph here, you see total cost in euros on the left, and then number of amplifiers in the chain across the bottom. 0 up to maximum of 10 amplifiers in the chain, which would bring us up to sort of 700 to 1,000 kilometers. The cheapest one, so just to explain here, we haven't included in this the cost of spectrum. So we're assuming that as an NREN, you've got a spare spectrum and you're not going to charge yourself a fee for using the spectrum on your fiber. So for that reason, the alien wave solution is essentially very cheap, because all you need is a White Rabbit switch at each end. You use the existing amplifiers. but has problems, not just in accuracy, but also in terms of maintenance, which I'll talk about later. Then the most expensive was the LSTAB. It's a high precision solution with specially designed amplifiers, and does give a very good performance, but it's not a performance that we evaluated here. So the remit remained for White Rabbit. So the 3 White Rabbit solutions, the most expensive was using White Rabbit switches at every site, and that's also, as it turns out, the least good stability, so probably not your best choice, especially for a long haul. The intermediate one was White Rabbit with amplifiers, so that's bidirectional amplifiers. So that's the solution that GÉANT trialed on our network. And then the cheapest of the 3 White Rabbit solutions was to have White Rabbit at each end and OEO regenerators at every site. You'll see for the White Rabbit and amplifier, there's a jump from 5 to 6 amplifiers, and that's because you need to put in a full White Rabbit switch or full regeneration halfway along. So apart from the theoretical costs in that spreadsheet, what does it actually really cost you? Just some caveats on that costing. The true cost will vary widely between NRENs, and you can put your own costs into the spreadsheet to find your own costs. The biggest one that's not included there is the spectrum cost, how much you want to kind of allocate as a cost from of use of spectrum in your DWDM system, and how many guard bands you choose to use, and how do you charge for those. So one thing to just keep in mind with guard bands, we recommend that you put White Rabbit at the edge of the C-band, because if you put it in the middle, you need a guard band on each side. But if you put it on the edge of the C-band, then you can just have a guard band on one side, and we'll save some spectrum costs. And as I said, you can use the cost calculator with your own costs. So regeneration costs will obviously be, as you've seen, highly dependent on the link length. So shorter systems below 5 links work quite well with amplifiers. But if they're really short and you only got 1 amplifier or something, you can just simplify your system, maybe just putting a White Rabbit switch, and then you reduce the number of different devices. You don't have to buy any OEO regenerators or amplifiers. So there's that cost. The other thing to keep in mind is the cost of managing the system. So the optical supervisory channel will need to be built if you're using an amplifier, a bidirectional amplifier. So typically you're in an amplifier site, you've got a bidirectional amplifier, and you've got no internet access in that site. So you will need to build a supervisory channel. So in the solution that we built for the GÉANT test, we had a small Ethernet switch, CWDM optics, and we sort of daisy chained those. Potentially, if you use a White Rabbit switch, you could use that as a management path, but you've got a slight problem that if White Rabbit switch breaks, you lose both your management and your time signals. So may not be an optimal solution. Typically, a DWDM amplifier will have an Ethernet port, but and they may provide inbuilt OSC. That is the case with the OBA3s. And if using a bidirectional amplifier with no on-site network, you need to budget for a dedicated optical supervisory channel. So not part of the cost calculator. The next thing to think about is operationalizing your network. A network which can't be operated, can't be used, is it's not functional. So we recommend considering carrier grade functionality such as dual power supplies, CLI for API for monitoring configuring. So that would be either on your White Rabbit switches, your OEOs, or your amplifiers. SNMP traps for alerting, remote management, temperature monitoring, and so the word from the White Rabbit Association is that they are looking into SNMP management for an open source style under the under the White Rabbit Agreement, but it's not yet been defined. In the case for GÉANT, we work with an integrator to keep spares to hold the amplifiers, because then we have to outsource. We don't have people on site, so think about spares and replacements. The other thing to think about with building a network is calibration. It's quite, as you will have picked up from Raimena's presentation, it's not entirely trivial. The calibration techniques are well documented by on GitLab there on that link. So the CERN people have done very good work on documenting that. So I can recommend looking at those calibration procedures. I don't want to repeat what Raimena said, but it's essentially the asymmetries. And the trick with asymmetries is if you go transmit and return on different fibers, when there's a fiber repair, the asymmetry can change. Now, if you go and return on a single fiber, there's a fiber repair, the asymmetry won't change in any significant way. But if you use it on different fibers, the asymmetry changes, so you will have to recalibrate, and that will really cause a big maintenance issue. So beware of just the temptation of using a very cheap alien wave service, because you may find that whole system becomes uncalibrated very quickly after maintenance events. The other thing to keep in mind is parasitic problems caused by lasing. So as I mentioned before, any excessive reflections and high gains in bidirectional amplifiers can cause lasing. That little diagram at the bottom is a sample from a spectrum analyzer I took on an experiment I was doing. These spikes, power spikes, appeared where there was lasing events. So best way is to use high grade angle connectors and keep the gain as low as possible. Don't forget cooling. For the long haul, you need high power, high DWDM grade SFPs. They can be much higher power dissipation than the CWDM ones, which the OEOs are designed for, and you can get you into trouble. So be very careful about OEO regenerators, so 2R regeneration for heat dissipation. So in conclusion, we have proven the coexistence of 1 gigabit White Rabbit on a DWDM system. We've got excellent stability demonstrated over 500 kilometers, well inside the 1 nanosecond target, and 3 regeneration options are available, and the best one will depend on each NREN. So thank you.